Hi, very good afternoon to all of you. Thank you for joining this session. My name is Shubham Gupta, and today we are here to discuss the need of shift in additive manufacturing education from basic machine operation towards manufacturing learning and the material understanding. Today, many institutions already have a 3D printers where students primarily learn those setups for basic machine operations like material loading, print part printing, or a basic prototyping. But an important question remains, are we preparing our students only for operating the machines, or are we enabling them to understand the material, the processes, and the manufacturing behavior? So, in this session, we will explore a material centric manufacturing learning approach and see how such platforms can support this shift in the education and enable students with the real manufacturing exposures, understanding the material behavior, and engage in sustainable circular learning practices that are aligned with the industry needs today. This is a 3D printing in education. Today's the scenario is this is a very common sight across institutions today. Many colleges have already established their idea labs, fab labs kind of facilities within the facility, and usually such type of facilities have one, two, or sometimes even more small FFF 3D printers. And within this setup, most of the engineering students learn about the basic machine operations, like they do loading of the material into the machine. They apply different slicing parameters. So depending upon the slicing program which they are using, they used to do the basic of printing, basic geometries kind of stuff, right? But they don't experience like what they're missing is also a very important point here. They never get a chance to handle the basic raw material, the feeding material which they are giving into the 3D printing machine. They never get a chance to handle the raw source of that material. They don't really see how the material behaves under different printing processes. If they are changing a certain extrusion rate, a printing parameters, they are changing what kind of material behavior changes has been happened. They never get a chance to experience that. And even when a print fails, the discussion usually stops at, okay, change the print settings, change the orientation, see the different support structure options, and reprint it. They never get a chance to think of what to do with that failed print. This is where the learning gap begins. This slide contrasts the difference between the two fundamental educational approaches. One is a machine centric education on the left side, if you can see, and on the other hand, we are talking of a manufacturing centric education. So I'll tell you the difference between these two approaches. In a machine centric education, student usually work with a filament as an input option, right? The material source is a type of a filament if I talk of an FFF kind of 3D printers. So filament in the form of a standard spools which are available in the market. It could be a general purpose materials like a PLA, PETG, or sometimes a ABS kind of material. And the focus remains limited on the design and geometric centric learning, right? What that means is they used to print the part with predefined materials. They will evaluate the part based on the application, and the application could be maybe a physical form and fit of that particular part. Sometimes it has to fit or do the assembly somewhere into another component, and in the last they will discard that particular part. So everything is limited, and there is a like limited approach towards the material interaction. On the other hand, if we are talking of a manufacturing centric education, there is basically the input material starts with the raw material level, the raw source of that material, and students understand the material behavior and the processes through which the material has to process during the fabrication process. And even they were able to understand the printing parameter plus the reuse application of that particular part, and how they can again reprint with that same particular material. So the reprintability, the reuse, the recyclability, which called it as a circular learning approach, they were able to understand in the manufacturing centric education. So we called this transition, we called it as a learning upgrade from a tool operation towards a manufacturing understanding. Now let's understand like why filament limits the learning opportunity. Filament-based 3D printing is excellent for rapid prototyping or for giving students an early exposure to the additive manufacturing field. It is a very good technology to start with. However, if I consider as an educational context, filament comes with a limitation. So the limitation I mean to say is the material which is used for printing is already processed form. Its composition is fixed. It has its own data sheet which has been made by testing a particular specimen at a certain conditions, right? So everything is pre-processed, everything is fixed. Because of this, students interact only with the final form of material. They are never getting a chance to check the raw material quality, to check the different parameters which are there in the raw material. So they did not get a opportunity to study how the raw material behaves during the melting, or how the processing decisions affects the final performance of the part. So as a result, the learning experience becomes largely geometry driven, as we discussed in the previous slide, and most of the time the focus of the students will be the printing capability. The print should be successful. Students learn how to make that part print successfully, but not why the material behaves the way it does in the printing process, right? Because real world decisions are driven as much on the material capability and the understanding of the processes. So the understanding of material science and manufacturing education becomes so important today. So to address all these limitations, we need to adopt a material first additive manufacturing approach, right? So imagine if instead of working with the pre-processed filament, which we discussed in a form of an ABS, PLA, or a PETG, what if students could directly feed the raw material into a 3D printing system, right? This is where the material-centric learning truly begins. So in a fused granule fabrication technology, we call it as a FGF technology. Students work directly with the plastic granules. It is the same feedstock material which is used in the traditional injection molding manufacturing processes or extrusion based manufacturing processes, right? So what that means is, instead of starting with a pre-processed filament that can uh, be coming in a specific composition, they can observe how the material melt, flow, and behave during the different extrusion processes at different temperatures, different screw speeds, and the different extrusion rates, right? This whole process allows students to understand about the material behavior, the process parameters, and the manufacturing logic, not just to print a geometry. So in a sense, FGF, or I would say fused granule fabrication technology, transforms the 3D printing from a prototyping activity into a true manufacturing learning experience. Other than that, there is a specific use case of pellet-based systems. It is for the material science education. So, as discussed, the filament composition in a filament, pre-processed filaments, the material composition is fixed. You can see in that image, right? So, students have very limited control over the additives of the material iterations. In contrast, if I talk of a pellet-based system, it gives direct access to the raw material, additives, and the recycled materials. So this allows students to study the melt flow, the shear behavior, and the thermal behaviors of experiment with the blends, and gain exposure to the real industrial polymer processing. For an example, like a student can use a virgin material and a recycled material in a controlled ratio and study how the recycling affects the material behavior and the part performance. This is a one use case, or it could be a one separate project entity for any student or the faculty. Other than that, students who are interested to experiment in the fiber filled materials, right? Fiber filled polymers, they can reinforce the polymer with a virgin material, reinforced fiber with a virgin material, and again could be a project based activity to work on the reinforced materials. The third project activity could be student can work directly with the real waste streams and understand the challenges of sustainable manufacturing. So likewise, these are the three general examples. There could be multiple different use cases with pallet-based system where a student or a faculty can develop their own material by mixing certain different materials at a complete composition level and can define the parameters, the properties of it for a new or an advanced applications. So this could be a one activity to work with the pallet-based systems. Now, this is the another one most overlooked questions in the 3D printing education. And the question is, what happens after the printing? What that mean is, what happens once the part get printed and or the project is finished, or what happens to the part which get failed, right? In most of the discussions, the answer is simply nothing. The part don't go back into the process, right? We cannot use it as a learning input. It simply becomes waste. Everyone often describe 3D printing as a less wasteful manufacturing process because unlike traditional subtractive methods where there is a block of material and we are cutting the material away from it wherever it is needed, in 3D printing, generally the material addition is happening layer by layer, right? And in principle, it is true. But in practice, 3D printing itself also creates a lot of waste in a form of there could be multiple failed prints. There are support structures during every print job. There are purge materials. There are test samples on a regular basis, and there are prototypes which never gets used. So even though we called it as a sustainable technology, the reality is it contributes to the global plastic waste challenge. So let's understand what are those numbers, like how the 3D printing is contributing into the plastic waste. First of all, there is no actually end of life defined for the 3D printed parts, right? So most of the waste, whether it is a support material or a prototype or a test print, it never gets recycled. It simply ends up in the landfill. I have some numbers from, this is a global report from 2020. Almost 18,000 tons of plastics were used or consumed as a 3D printing in the 3D printing industry. So this number is a whole number of all those different technologies, be it FFF, the wire-based technology, or a resin-based technology, or a powder-based technology. Out of this, if we consider one third as a waste in terms of the printed prototypes which are not getting used, almost 6,000 tons of failed prints of discarded materials which are considered as a 3D printing waste. And remember, the 3D printing material industry itself is growing 25% every year. So the waste is even compounding rapidly, right? So even though we call 3D printing as an efficient process, but we still have a growing waste problem to solve here. So in reality, achieving zero waste 3D printing is almost impossible. And when waste cannot be avoided, most people think let's recycle it, right? So it sounds great in theory, but when you try to look closely, filament recycling is not as straightforward as it seems, right? The process involves multiple stages. The first stage could be the cleaning, the sorting of that waste material, then the remelting of that plastic, extruding it into a new filament, and then testing every batch. And even then, we can still face issues like the quality loss, the contamination, material contamination, or the scalability of it. So While recycling is an important factor to consider, but it is not as practical or not as efficient at a scale, right? That's why we need to start thinking in terms of a circular economy where the waste is not just managed, but we can reused in some way that it becomes directly as a feedstock for our new prints. And this is where the palette-based 3D printing approach truly stands out here. So it skips the whole manufacturing of the filament, allows you to recycle and reuse the material directly, efficiently into your 3D printing system, right? And by eliminating the filament making process, we are not only reducing the plastic waste, we are reducing the cost, the material waste, and also open the door to using industrial grade and recycled polymers right into the printer. There are a lot of applications which we can open up with such scenario. The biocrate system does not just print it, it completes the entire cycle of reuse. Let's consider the sustainability through the pellet 3D printing. So whatever will be the waste model, your waste model or a waste part, it which gets failed or the leftover plastic, it goes into a crusher, it gets pelletized into small crushed plastic elements and is then become the input of your same 3D printer. What that means is whatever the crushed particles is, crushed plastic elements, you can directly fed it into the 3D printer and it will get melted and again you can reuse it for your other project activities. What that means is the entire waste becomes the input source of your new 3D print and it eliminates the whole process of filament making. So consider now such setup in your lab. Your lab becomes a mini micro factory, which basically, if it is generating a waste, you are recycling it into some other way, right? This whole process can eliminate the need of filament extrusion and reducing the cost as well as carbon footprint. So along with that, it is not just a product but a solution with purpose, empowering industries to turn plastic waste into a usable product. I have a video over here with a similar use case where the recycled PLA material has been used and crushed it into a small particles and then it becomes a feeding input for the new prints.
In a time where we strive for green and sustainable solutions, we've chosen the G5 Ultra. Prints any part we need at high speed and with stability. We're using RPLA recycled material, a reusable and degradable eco-friendly material. It's not just a choice, it's an attitude, a respect for our planet. But the potential of G5 Ultra isn't limited to this. It can print a variety of recycled materials. This is our future, this is our responsibility.
So this is the company which used almost 1,000 kg of recycled or a waste product, I would say, and turns it into a recycled material, which becomes the again a useful product for some other use cases, right? So this kind of project activity could be done in an education scenario where a faculty along with a team of students doing similar sort of activities, or if you have a lot of prints, the waste prints, you can turn it into a micro factory as we discussed in a previous slide and can use those waste prints as a feeding input for your next new applications.
In a time.
So the setup or the solution which we are talking over here is from a company called Biocreate. And the model is G5 Ultra. If you can see the image over here, so the system looks like this. There is a hopper on the top where you will basically fed the material, the raw material. It could be in the form of the raw pellets, or it could be the crushed particles, the plastic waste material which we are talking. So it has a certain storage capacity. Through the feeding tube, all those pellets, the raw material get fed into the extrusion system. The extrusion system here is called a screw-based extrusion system. It's typically the similar to the injection molding screw-based mechanism, right, which we have seen in the traditional processes. And with the help of a heating mechanism, so it has again basically multiple heating zones. So I have shown it in my coming slide as well. So up to 420 degree of Celsius the nozzle can reach, right? So depending upon the type of the material and depending upon the slicing settings which a user has done, the material will get start melted up. It first of all it get pressed through a barrel, and with the multiple heating zones, that material allowing to progressively heat up and melt. And the pressure build up within the extruder forces that melted material out of the nozzle, and layer by layer the printing will happen depending upon the type of the geometry, the type of the orientation which you have done, the printing will begin. Certain other parameters of the machine, the nozzle temperature we discussed is maximum temperature is 420 degrees Celsius, which enables the printing of engineering grade materials such as polycarbonate, PA, or composite materials like carbon fiber, glass fiber. You can even mix the different materials, the virgin materials, with composites in a controlled ratio to define your own material for certain applications, right? It offers you a good build volume of 500 by 500, which not only used for prototyping, but you can able to print functional parts, mold, or large scale prototypes depending upon the applications. I have one more video to showcase the type of models which has been printed on a pellet based system.
This material is ABS with carbon
This is
fiber.
the ABS carbon fiber material.
Here is PTG, which is recycled pipe.
Recycled PETG.
Carbon fiber materials.
Again, a composite material, carbon fiber.
PU.
The flexible elastomeric material.
This PTG. TPU. Here's the details of printing. Lamp. Colorful chairs. Recycled PTG chairs was exhibited in the exhibition by our clients.
Some of the sculpture models.
Sculptures. Printed in different parts and assembly.
Right. So this video explains the type of different models in terms of build volume and the type of different materials which are feasible to print with such pellet-based 3D printing setup. Not only that, the Biocrate itself has a library of materials with specific materials like a PLA, ABS, DPU available in a granules form, as well as certain composite materials like polycarbonate with carbon fiber blend, ABS with carbon fiber blend, again a PETZ with a carbon fiber blend also. Other than that, there are other different materials which are able to successfully print on such a setup for research purposes or for general purpose applications. So this video will describe the list of different materials which have been tested, like ABS carbon fiber, PETG blend with the glass fiber as a composite, the standard PLA material in a multicolor TPE, TPV type of material, TPU for flexible applications, metal, alumina, zirconia kind of stuff. Why? Because the temperature of the nozzle could reach up to 420 degrees Celsius, which is generally not available in a, I would say, desktop FFF machines. Generally, FDM FFF based 3D printers comes with a temperature range of 300, 310 degrees Celsius and limited to materials like ABS, PLA, or PETG. Here you have a chance or an opportunity to work with the first of all the raw feeding material, which is traditionally being used in the manufacturing processes, and to make a blend of those materials in a different controlled ratios so that you can define your own material with certain applications. So comparing to the filament printers versus the pellet based printer, definitely the price of the filament or the raw material will get reduced here comparing to what is available in the market. There is a material freedom, a completely open based systems where you can blend different materials and can test it out. Recycling or sustainability, where you are getting a chance to do the recycling research of your waste material, right? So these are a couple of different use cases or the advantages of the pellet based system over the filament based systems which are being traditionally used in the education industry. So what FGF enables in education scenario? These are the 5 points which we have discussed so far in our slides. I'll just quickly cover it. The first was is the opportunity to directly use the granules material, which is the same feedstock used in injection molding or extrusion based processes. The second advantage is the it enables the hands-on research, right? So in process engineering or the material sciences, where a student and faculty have an opportunity to work on their own new developed materials by mixing certain materials. They have the opportunity to work with could be a project activity. Third advantage is the material cost reduction up to 70% compared to the filament based printing, which is generally available in the market, the generally available traditional materials which are there. Scalable due to the large build volume. General build volumes of the FFF machines are in the typical range of 250 mm cube, 300 mm cube. Here you are getting a massive build volume of 500 by 500, so that you can support the large parts high throughput also. High throughput, I mean to say, is in general the FFF machines comes with a nozzle size of 0.4 mm, which is a very standard sizes, right? In pellet, since you are directly feeding the raw material in the form of granules, and these machines are meant for large parts, you have the option to upgrade the nozzles up to a size of 1.2 mm. You have a 0.5, 0.8, 1.2 mm nozzles, 2 mm nozzles, so that there is a high throughput while printing a certain large parts, right? And the fifth advantage is the recyclability, as we discussed, which helps and enables you for a circular and sustainability learning practices. So beyond academics, the pellet-based systems are being used in industry as well for multiple applications. Prototyping is a very common application in 3D printing, be it any machine. Prototyping remains the first and the major application in additive manufacturing. Other than that, the tooling patterns, since they are also bulky, big in volume and sizes, jig fixture applications, production scenarios like furniture also we have seen in the video. A couple of medical applications, the patient-specific assistive devices. There are certain medical machines as well as medical materials in a form of raw pellets are available within this pellet-based system, which can be used for medical-based application. So likewise, could be a multiple project activities in education scenario where you can work jointly with the industry, or the student faculty itself can jointly work on a project which can have in a different application scenarios. So why choose FGF pellet 3D printers? Cost reduction during printing because of the raw material input, shorter lead time because of the faster throughput, high throughput through the pellet-based system, excellent material properties, opportunity to work on open source platforms to develop your own materials without developing the whole filament process, right? Which we have discussed of melting, extruding into a filament, cleaning, and testing. And the fourth is a eco-friendly by sustainability, recycled plastic, and other additive manufacturing alternatives. So before we close, I would like to briefly share that additive manufacturing is just one part of the solution we offer. As a company, we work closely with educational institute to support the entire digital manufacturing and industry 4.0 learning platform. This includes the design and simulation platforms, the 3D digitization and scanner options, additive manufacturing in terms of multiple technologies, collaborative robotics, and automation and autonomous system training. Our objective is to help institute build integrated learning environment based on their curriculum goals, student skill levels, and future industry requirements. Thank you for your time and attention. I would like to leave you with a one key thought. Additive manufacturing in education should go beyond teaching students how to operate a machine. Right? It should help them to understand the materials, the processes, and the manufacturing behavior, because that is how a real world engineering decisions are made. A material first approach allows institutions to transform the 3D printing labs into a manufacturing research sustainability learning environments. Whether it is introducing students to a raw material or enabling circular learning approach, or preparing them for industry or research goals, this shift adds long-term value to the engineering education. Once again, thank you for your time and attention here. I will now be happy to take your queries, if any. Thank you.
Yes, Shubham, there are some queries from Mr. Vedant. So, will it make ever weaker material?
Sorry?
Will it make ever weaker material? Even weaker material.
I did not understood your question, sir. Will it be able to make a weaker material? I'll tell you the idea behind this technology so that it will clarify, I think, your question. So the idea is instead of using the pre-processed filaments which are there in the market in a form of like PLA, ABS, which is being used in an FFF machines, the product here we are offering beyond the traditional way of 3D printing is a FGF based 3D printing technology, which used raw material as a form of a granules. So the granules could be of a PLA, ABS, or a composite, right? You can take the two different granules, mix it in a controlled ratio, and can make your own material out of it for the testing purposes. So this is the whole idea behind it, which enables the first thing is a research project activities in an education, as well as there is an opportunity to use the recycled material, the second best example or a use case for FGF systems. where in a filament, if we have to make a filament, there is a whole way of lengthy process, and the success rate is very minimal, or it is very tedious task to make a filament, a recycled filament, right? Instead of that, here we can just crush it, clean and crush it, and can become those crushed part will become an input here in FGF. So this is a whole scenario. Just in case if there is any further query related to that, you can write it to us so that we can directly discuss on the specific requirement and can help you out. Any other questions?
Yes, so one more question from Mr. Vishwant. Limitations, things that FFF does better.
Limitations that FFF does better?
Yeah, limitations or things that FFF does better.
Limitations or things that FFF does better. Limitations, I would say, limitations we discussed here in our session. Limitations, the first was the material input was the limitation, and like FFF machines does not enables you to research activities. Here FCF has that option. High throughput in FGF versus the speed, I would say the FFF machines are bit slower than comparing to FGF when we talk of the pellet based system, because of the bigger nozzle size, right? So these are the major advantages or limitations, I would say, here in FFF or FGF. Advantage of FFF is you have a pre-processed filament, you can directly feed and start printing. Here you may have to tweak certain parameters depending upon what sort of material or pellets you are inserting here in the FGF technology. So those tweaks you have to do, but there are a lot of endless possibilities with pellet-based systems. Any questions further? There are more questions I can see in the chat. Which filament types are supported? So the first thing is the FGF machine is not based off filament. So here you are actually the advantage here is we are not using the filament. We are directly feeding the raw materials of pellets in a form of pellets. So those pellets like which we have seen in the traditional way of manufacturing of injection molding or extrusion processes. So directly those pellets we are feeding here, right? So those could be of anything like PLA, ABS, blend of composites. The nozzle temperature is 420 degrees Celsius. So almost every type of polymer material is able to feed it in the FGF technology. The printing resolution and the printing speed is the another question. So as I discussed in my slides, the nozzle size is 0.5 mm and the layer resolution we can start is at 200 micron, 0.2 mm layer height we can choose. And accordingly we can go up till 1 mm. 1.2 mm ka nozzle sizes and layer height accordingly will be to 0.6 mm. So if we are using 0.5 mm, the minimum size of nozzle, the real printing resolution will be almost similar, which you can see in the typical FFF machines with 0.4 mm nozzle. Let's say you are printing a very big part, or the part doesn't have a critical feature, small details, and you want to print it very quickly, FGF will help you in this scenario with the bigger nozzle sizes of 1.2 mm or 2 mm. So I hope I have answered your query. Do you have slicer applications associated with printer? Yes, the printer comes with their own slicing package called BioCrate Slicer. So it helps you to again doing all that stuff of part orientation, support generation, different print settings in terms of speed, extrusion rate and other stuff. So it has its own dedicated slicing software which can be used. We are in the manufacture of automobile clips. How can we scale to take production in large quantity? So a large quantity, it must have a certain number. Um, uh, uh, this FGF technology could be helpful in your use case in automobile clips. However, if not, we have the different, I would say, technologies for large quantity printing applications. Right? I mean to say a batch production scenario. So you want to print 5,000 components, small components, 10,000 components, 15,000 components in 3D printing with end-use material, which can be directly used for various applications. We have those solutions. You can reach to us directly so that we can work on case by case. Are there any post-process to use with FGF from sanding and painting? Consider poor surface finish with recycled material. Yes, definitely. If the surface finish is the criteria, you can use the standard post-processing techniques like sanding, painting, buffing, or so. So since it is a plastic material, all those traditional approach of post-processing works with FGF as well. So definitely we can go with that if poor surface finish is the concern. How easy it is to replace the part nozzle fan? It is as easy as if you have done in your FFF machine. The nozzle size is same, so one screw you have to like take it up and put the nozzle. So it is as simple as that. We have we dedicated videos as well of replacing these such kind of parts or maintenance activities. You can reach out to us. We will share you those details. And what is the minimum and the maximum layer height? That I answered already. Minimum layer height is 0.2 mm with the nozzle size of 0.5 mm, and it goes up to 1 mm layer height with a nozzle size of 2 mm. Right? What kind of preheating system is there? Preheating, the build plate is preheated up to a temperature of 120 degrees Celsius. Nozzle could reach up to 420 degrees Celsius. Along with that, it comes with a isolated cover system. So you can basically make it as an enclosed 3D printing system to print high temperature materials. Like if the temperature requirement is 300, 320, 400 degrees Celsius, to maintain those temperature levels, you can make it as an enclosed system. So it comes with a cover also. Does this technology align with the Industry 4.0 curriculum development? Definitely. 3D printing is a part of Industry 4.0, and FGF over and above gives you an opportunity to work with directly raw material, recyclability, sustainability. All these parameters are the part of Industry 4.0 curriculum. Cost of the machine, you can reach out to us. We can work jointly to see the opportunity and the requirement, and accordingly we can work with that. We recyclable the waste material of 3D printed parts, make weaker parts when you print it again. That is the project activity which a student or a faculty can do. How recyclability affect the part performance is the criteria. Definitely, if we are using a recyclable material versus a virgin material, there is a weaker part performance. Yes, but if you are mixing a virgin material with a recyclable material in a controlled ratio and do a project activity and see how it behaves or how it acts, is the actual use case of this setup in an education, right? Since most of the institutes has the FFF based machines, so this technology brings you an experimental approach of such scenarios, right? So, who is the pioneer of FGF printer? Example, Apple for computer, okay. Bamboo is for FDM, correct. If you have heard of a company called Creality, in FDM 3D printers, it's a well-known company. So the Biograde is a child company of Creality. So Creality is a well-known, famous company for FFF-based 3D printing systems. So the product which we are offering, the Biograde, is from the same brand. The raw material for 3D printing comes in a filament form. Pellet form is not available. The damaged prints of manufacturing waste have to be converted into pellets. Mainly the scraps are mixed. It will be difficult to control. Okay, there are two questions here. The raw material for the 3D printing comes in a filament form. Pellet form is not available. No, it is not like that. For FFF machines, definitely the filament is the input. But for pellet machines, there are granules. It comes in a form of pellet. Like as I shown in my presentation also, we have a built-in library of different materials which we offer as in a pellet form. Even you can source those pellets locally in India. There are companies who are making pellets, or the pellets which you are using for injection molding machines can be directly fed it here. And if you are mixing the scrap like PLA, TPU, ABS, yes, the chemistry will affect. The agenda is to mix one sort of material like a recycled PLA or a recycled ABS kind of thing. If you are mixing, definitely again it will be a project activity, become a project activity of mixing two materials and how it is affecting the part performance, or how well those two materials behave, how well the chemistry of those two materials behave while mixing could be a research opportunity here. Does the printer support open source firmware or customization? Open source firmware or customization, for what purpose? I did not understood. Please reach out to us for your specific query so that we could help you to answer this. Can this 3D printer be used for developing new material blends or recycled polymers? Yes, this is a major use case of this 3D printer for developing new materials or recycled polymers. Are you planning to host or join any industry exhibition? Could be, yes. However, if you have to see this machine in person, we have installed it in our Bangalore office. Whosoever coming to Bangalore can directly reach out to us and can visit our facility to see in person this particular machine. And if we are participating in any exhibition where we are displaying this facility, we will definitely inform you through our social media platforms. I hope I answered all the questions or queries which has been raised. Further, if there is any question which is left or unanswered, please write it to us. We will definitely share, like help you to solve your query, and we'll share these slides whichever I have shown a couple of videos, whosoever have attended and registered to our this webinar session. Thank you. Any other pending question left, Swati?
No, we answered all. Anyone, if any question is there, you can post now.
Okay, I think there is no further question. However, if it is so, you can directly reach out to us with your queries. Thank you. Thank you once again for joining this session, and much appreciated.
Thank you, everyone. Thank you, Mr. Shubham. And I have posted the contact number and email and website. Everybody, if any further query is there, please reach out to us. Thank you so much.